Greetings, Chem Fam. Today we're going to be looking at percent yield worksheet number 1, trying to figure out, first of all, hey, what is the limiting reactant? Once we know the limiting reactant, we can then figure out, okay, how much theoretically, according to the math, should we produce of the product? And then from there, compare how much we should have gotten because the math tells us versus what we actually got in the lab. Just a quick reminder that percent yield has an equation to it. And remember, it's just simply the actual amount of product that we got from the lab, right? And we're going to divide that by the expected amount, and that comes from not the lab like we would do in class, but that comes from the math, all right? And that slash there is not like a divide sign. I don't want to confuse you guys. I'm going to erase that. That is just from the math. So the actual lab value versus the expected value that we got from the math. So let's take a look. It says determine the percent yield for the reaction. So eventually we're going to use this equation for percent yield. And let's see, it's between 6.92 grams of potassium and 4.28 grams of oxygen if this much K2O is produced. Now, right off the bat, the 7.36 grams of K2O, they're telling this is what we got in the lab. So already we know the actual value. We're not going to use this value for any of our math and stoichiometry, but we will need it for our final step when it comes to plugging into the percent yield. So keep that in mind. Now, this problem, I should say, not equation, tells us that potassium and oxygen are going to react to produce one thing, which is K2O. So right from the word, we can figure out our balanced equation already. Speaking of words, I'm having trouble with mine this morning, but that's all right. So we are going to balance that out. There's 2 oxygen on the reactant side, so I'm going to need a 2 there to make 2 oxygen. That's now going to make 4 potassium, so I'm going to put a 4 there. Looks like I'm going to balance out with a 4, 1, 2. Now looking forward, what do we need to do? Well, in order to get the percent yield, our next step is going to figure out what's the expected value of the product. You know, how much can we expect? So that's theoretically, if the stoichiometry we were using, how much should we expect to get? Even though we know in the end, in real life, this person got 7.36 grams from the lab. So let's compare what they got in the lab to what theoretically we should get, which is from the math. So to do that, that's just going to be a limiting reactant problem. We're going to take our 2 reactants. So I've got 6.92 grams of potassium, and I also have 4.28 grams of oxygen. And what am I going to do? I'm going to convert both of those into the mass of the product, which is K2O. We know that's produced at the end. Now, the reason I'm doing that is because I need to figure out from the math, how much are we expecting to get? Because remember, the expected value is what we're going to have in the bottom of that equation for percent yield. So now that I do that, I know from mass to mass, I'm going to convert my mass of A, or reactants, to mass of B, the products. So now we're just going to do our stoichiometry. In order to do that, I'm going to use my mole map, but I know for every 1 mole of potassium, according to the periodic table, there's 39.10 grams of potassium. Got that from the periodic table. Next is mole A to mole B, which means B over A moles. My A object is potassium, that's what I started with. My B object is going to be K2O, because that's what I'm ending with. I'm going to look on my map here, or I should say my balanced equation. There are 2 moles, MOL, of K2O for every 4 moles of potassium. So I'm going to put a 4 there. Next, I just have to convert then my moles of K2O to mass. So I'm going to put 1 mole of K2O on the bottom for every gram of K2O up on top. And let me see what the molar mass is up top. If I add 2 potassiums and 1 oxygen up, I'm going to end up with about 94.2 grams. Now that I have that, stoichiometry says I'm going to take my number, multiply by the top, divide by the bottom, multiply by 2, divide by 4, multiply by 94.2, divide by 1, So multiply by top, divide by the bottom, and the answer I end up getting for that one is about 8.34 grams. Okay, so now that I know that mass, I have to compare it to how much mass we would get of K2O if we used up all the oxygen, O2. So we have to redo that problem again, but now for oxygen. So for every 1 mole of O2, oxygen, according to the periodic table, there's 32 grams when you add up 2 oxygen. So that's my molar mass on the bottom. Now I'm going to go from moles of A to moles B, which means according to my mole map, I'm going to do B over A moles. Obviously, our B object is our product, K2O. And I know there's 2 moles of that according to my balanced equation. And for oxygen, it's going to be 1 mole of oxygen on the bottom because there's only 1 in the balanced equation. And my A object that I start with is O2. That's why it goes on the bottom versus K2O, which is my B. Now that I have that, I'm going to do the same step I did with the problem above. For every 1 mole of K2O, there's going to be 94.2 grams of K2O. How do I know that? Well, I'm just going to add up 2 potassiums and 1 oxygen for the molar mass. And when I do my stoichiometry, multiply by top, divide by the bottom, I end up getting an answer that is about 25.19 grams. 25.19 grams of K2O. All right, from there, we have to determine then what is the true value we should get at the end. Well, if you used up all potassium, you would only make 8.34 grams of K2O. If you use up all the oxygen, it says you'd make 25 grams of K2O. Well, which one is going to run out first? Obviously, our limiting reactant is going to be K. K is our LR, our limiting reactant, potassium. Why? Because it creates the smallest amount of product, so that must run out first. So now that we know this value, what is this? This is going to be our expected value for percent yield, which is going to go on the bottom here. So to do my percent yield problem, percent yield is going to be equal to, up top here is the actual lab value. Remember that came from our word problem, so that's 7.36, okay? And then I'm gonna divide by the expected value we got from math, which we just determined was right here, the smaller value, 8.34. Now don't forget, I overwrote a little bit. I'm going to erase this. We also want to divide it and then also multiply by 100 because we want to get it into a decimal form for percent. So 7.36 divided by 8.34 ends up being about 88.25%. Now, what does that mean? That means that we expected to get about 8.34 grams of the product, but we only got 7.36 grams. So we got about 88% of what we expected. Why didn't we get 100%? Well, in a lab, there could be many reasons. You accidentally measured wrong. You didn't let the actual chemical reaction react all the way. Maybe you stopped it too soon. Maybe when you were collecting the product, at the end, you accidentally spilled a little bit and lost some of the product. So there's a lot of reasons why it's not 100%, but in the end, your percent yield was 88% of what we expected from the math. That's why we call the math value the expected value. The math doesn't lie. It tells you what should happen, but the actual lab value is what really did happen in the lab because we're humans and nothing is perfect. All right? So that was problem number 1 to get you going with finding your percent yield. Now that we've done number 1, let's crush number 2 together. So again, you're going to be looking for the percent yield of the reaction between 3.74 grams of sodium and excess oxygen. Now, let me just tell you, we love when a reactant, they say there's excess oxygen. That means there's extra. That means it won't run out. So if it doesn't run out, that automatically means that the other reactant, Na or sodium, is the limiting reactant. So what does that mean? It means we can do less problems. We don't have to worry about how much oxygen is going to create in the product because we know that's not the one that limits the production. So sodium is going to be the one, Na, that limits it for us. So that's great. You're going to see in a second how that speeds up our process. Now, it does say that this much is created at the end. So remember, if that's the case, then this is our actual value that we got from the lab that we recovered. So that's going to be in our percent yield problem. But first, let's do our balanced equation. It said sodium Na is going to react with oxygen, O2, to make Na2O2. Looks like I just got to put a 2 there to balance it out, and I think we're good, 2 on each side. Now, normally we do 2 problems to figure out what the limiting reactant is and what the product that would be formed is. But we don't need to because we already know sodium is going to run out first because we have excess oxygen. Excess means extra. There's so much, we're going to have overflowing amounts, so we don't have to worry about it. So all we have to do is take our reactant and do what we always do. We're still going to convert it to our final product, which is Na2O2, sodium oxide. But isn't that beautiful? We only have to do one stoichiometry problem now. We love that. So let's do this. Let's convert. The reason that we want to convert this to grams of Na2O is because this is going to give us our expected value. And remember, in a percent yield equation, right? Percent yield, put this on the bottom so we keep an eye on the prize. It's going to be the actual amount of product divided by the expected amount of product. And just don't forget to multiply by 100. Perfect, let's do it. I'm gonna go from mass of A to mole of A. So the first thing I need to do is convert mass of A to mole of A. And to do that, I am going to divide by the molar mass. I'm gonna look on my periodic table. According to my periodic table, the mass of 1 sodium is 22.99 grams, right? So 1 mole of sodium is 22.99 grams. I'm then going to go from moles of A to B, which means I'm going to put B over A moles. Sodium is going to go on the bottom. My product, the thing I'm solving for, is going to go on top. If I look, sodium has a 1 in the balanced equation, so I'm going to do 1 mole for every 2 moles of sodium. So there's a 1 on top, 2 on the bottom. And my last step is going to convert my moles of the product, Na2O2, sodium oxide, into grams of it so that I can get my expected value. I'm going to add up 2 sodiums plus 2 oxygens. If you add those up off the periodic table, it ends up being about 77.98 grams. All right, do your stoichiometry. Take your number 3.74, multiply 1 by 1, divide by 22.99, times 1, divided by 2, times 77.98, divided by 1. Don't forget you can also skip the 1s. Right? They don't really change the answer. But what I end up getting for this one is 6.34 grams. All right, what does that mean? That means it's our expected value. So, to get percent yield, I need to do actual over expected. Actual value was given to us, 5.34 grams. It set it up there that it was recovered. So that's what we can assume they got in the lab. Now, according to math, we should have gotten about 6.34 grams. So we didn't get as much as we expected, but that's normal. Getting 100% yield is really hard in a chemistry lab. So let's do this though. 5.34 divided by 6.34. Hit that enter button, multiply it by 100. And I end up getting about 84.23% yield. What does that mean? It means we got about 84% of what we were expecting to get. So pretty good lab. You only lost about 15% of what you were supposed to get. And again, that could be chalked up to human error, accidentally spilling. When you measured out, maybe you didn't zero something right. Maybe the reaction didn't go all the way through. Maybe you didn't heat enough so that it would happen. There's a lot of reasons, but part of the fun of chemistry is kind of figuring out those mistakes. And if you did this over and over again, you could get better and better results. And that's what a company would do. They would say, why are we only getting 84%? How do we get it to 95%? What little things can we do to make a better impact on making this reaction go all the way through? But anyways, there's 2 big examples of percent yield, taking all the skills you know already. Balance the equation, find the limiting reactant, which is awesome. Sometimes they give us that option. Take that limiting reactant, use it to predict how much is expected, and then plug that into your percent yield equation so you can get your final percent yield to figure out how much you actually got compared to what was expected. All right, well done, fam. Keep up the good work.